Welcome, my dear J26 aspirants, all my dropper friends, and my class 12 aspirants. So, today we are going to start with the electrical potential energy and electrical potential. We are also going to see the equipotential surfaces and equipotential lines concept and how what we have learned previously, which is electric field, how is that electric field related to electric potential? And many students often get confused between potential and potential energy. That confusion will also be cleared. So all of this in today's session with me on your number one J English channel in the country, Vedantu J English. And this is your Captain Shreyas, your physics master teacher, teaching for more than 13 years, sending a lot of kids to their dream engineering colleges, be it IITs, NITs, BITS, you name it. So stay subscribed. And if you have not yet marked your attendance, please do that right away, right now. And last lecture, you can see we have done electric fields and field lines. Make sure you're completing all the lectures. Before this, we had done Coulomb's forces, superposition, and homework also is given. Make sure you are solving the homework question and putting it in the comments. Yeah, I want to see more and more students participating. Don't think, sir, it's okay, answer is already given. No, PDF link will be shared after the session is over. Like this, you click on this particular link in the comments or in the description box. You can see the entire PDF, handwritten annotations, everything. Very good, A to Z. Durga, very good, Yasasvi, sorry, and Vignesh. Perfect, very nice. You guys are answering correctly or not, that is not important. You should be solving, that is more important. If you answer incorrectly, you will learn from it. Okay, and answers, everything are there in the PDF. It's there. Okay, sir, my videos after the advanced exam will cover the syllabus before JEE main of this year. Yes, Jack. With the target is, you have to cover everything by October, not even December, by October. Yeah, welcome, useful facts. Thank you for all the hearts. Good evening, Pratiksha. Nice to see. Hi, Aruneshwar, Vignesh. Good evening, good evening, good evening. So let's begin with the concept. Now, see guys, remember the word potential energy stands for, capacity of doing work. It is a stored form of energy. So if I just ignore this particular aspect from the picture, then we know potential energy is a stored form of energy and it has capacity of doing work due to its configuration or arrangement, due to its configuration or how it has been arranged, like a compressed spring. The way it has been arranged, it has some potential energy. Magnets brought to close to each other because of that arrangement have capacity of doing work, so they have potential energy. And it is always, remember, it is always associated with something called as conservative forces only, with conservative forces. Now, if you have forgotten the meaning of the word conservative forces, basically the total work done in a closed path should be zero. Yeah, the total work is zero in a closed path. That means you come back to the same place, the net work done should be zero. It is true for gravitation, spring, elastic forces, even electric forces for that matter. And if you go from point A to point B via two different paths, the work done in path 1 or in path 2 will be the same. It is basically independent of the path. It is basically independent of the path. These were some essential things regarding potential energy of class 11th. I need to revise this or else you might face some issues in concepts. Also, it's there in the 11th standard work per energy chapter. Any kind of conservative force is related to its associated potential energy by this formula, negative du by dx or du by dr. This is the relation between them. If you take dr over here, force into displacement becomes work. So you can also say the work done by that conservative force is basically the negative of the change in the potential energy, because displacement into force is the work. So this is also going to be true. This is not just true for electrostatics, guys. This is also true for gravitation, spring, elastic, magnetism, everywhere. Uh, uh, as soon as you see conservative force, you should use it. Okay, this was something like a recap, you can say, of 11th standard. Are you remembering this? Yeah. Pratap, yes, of course, this is a lecture for JEE only. This is a JEE channel. Obviously, it will be enough for JEE. Yeah. All right. Okay. Now, if this is something which you remember, or if this is something which you have, recollected, good. If not, then I would suggest you to watch any of my older lectures from the channel, from work, power, energy. You can just search for work and energy over here. You can definitely get my older classes also, like it is there over here. What is work, power, energy? Old classes also perfectly fine. Even the roar series also you can watch. Okay, it is explained over there. Okay. Hi Nagaraju. Now that we understand, okay, the rate of change of potential energy with respect to displacement is the force, or the negative of the change of the potential energy is the work done by the conservative force. Let's proceed ahead. Just to give you an example of this, just to give you some example of this, very, very important. Say for example, I move somebody from here like this to over here. In this process, let's say some conservative force was acting, some conservative force was acting, and the work done, the work by the conservative force, say for example, happens to be maybe 20 joules. If it is 20 joules, remember, whatever is that work done by the conservative force is the negative of du. That means it is that 20 joules is also the negative of the change in potential energy. Therefore, the change in the potential energy, take that negative side over there, is minus 20 joules. That is how it works. Okay, whatever is the work done by that force exactly is negative of the changes in the potential energy. Usually the symbol for potential energy is U. U is the capital U is the symbol. We do not use P dot E dot because then it might look like P into E, and P stands for dipole moment, E stands for electric field. So it can lead to some confusion. So that's why we preferably use the symbol capital U for that purpose. Okay. Now, also remember, there is one interesting thing over here. This value also happens to be, if you just take this minus sign onto this side, okay, if you just take this minus sign onto this side, so it will now become negative of the work done by the conservative force. One and the same thing, guys. It's one and the same thing. This, if you take it over here, also is the work done by the external force, is also the work done by the external force. This is a more generic rule which you can use in many places. If external force does 10 joules of energy, meaning imagine I was lifting my phone and I do 10 joules of work, I am external. That 10 joules will go sit inside the gravitational energy. Think about it. If I do 10 joules of work, that will go sit inside the potential energy. All that work goes into potential energy. So if I do 10 joules of work, the increase in the gravitational potential energy would be 10 joules. At the same moment, gravitational force would be acting down. Think about it as I'm lifting my phone. So that force will be doing negative work. And how much negative work? Exactly negative 10 joules. So if I do 10 joules, gravity will say, I will do negative 10 joules of work. Negative means you are sucking that energy. And all that energy which has been sucked will get stored in the potential energy. All these concepts are very important before you start the concept of electric potential energy. Yeah? Megasham, I'm perfectly fine. Yes. All right. Okay. D. Sharma Tejas, don't break the flow of the class. Whatever your queries are there, put it in the comments. We'll answer it. Okay. All right. Definitely, Anburaja. Obviously, I'm there for all the JEE aspirants. I take many classes, even the things which you do not see. You might not know. Many things are there, many batches are there, many recordings are there. All for you. Okay. So, this is very important. So, my dear warriors, in case the question was, what is the work done by the external force? What is the work by external force? The work by the external force, as you can see, is exactly the change in the potential energy. That means it will be also negative 20 joules. So anytime any of these three things are given to you, you should be able to calculate the other thing. If du is given, you should be able to calculate this or this. If this is given, this or this. If this is given, this or this. Any of these three things, one of them is given, you can calculate the other two. Is this clear? So very, very important, my dear students. One more example which I can give you. Say for example, I bring two, or let's say I let go, or let's say I am taking some box over here and I'm taking it up. So let's say the external work done in this case is plus maybe 15 joules, plus 15 joules. So gravity, which is a conservative force, the gravitational work will be exactly negative 15 joules, and the change in the potential energy of gravitational potential energy will be exactly 15 joules. So whatever work you did goes and sits inside the potential energy, and the gravitational work is sucking away all that work from external agent and storing it faithfully inside potential energy. That's why that negative sign comes. So this is the main basic understanding. If you understood it till here, please give me a thumbs up. Please give me a thumbs up if you understood it till here. Then we'll proceed to electrical potential energy concept. Then we'll proceed towards the concept of electrical potential energy, guys. Everyone? Yeah? Sure? Okay, so let's begin. So how do I define electrical potential energy? It is nothing but the electrical form of stored energy between charges, and the manner in which it has been defined is as follows. The electrical potential energy U is nothing but the work done to assemble the charge system from infinity. See, always whenever we talk about potential energy, it is always with respect to something. You never have an absolute value of potential energy, because you always choose something as 0. So when I say my position is 5 meters, x is equal to 5, you know x is equal to 5 is with respect to the position where you have assumed it as 0, origin. So there is some reference point. So from that reference point, I am standing on a line called as the x-axis at 5 meters. Same thing happens with potential energy. When I say mgh is not absolute value. It is with respect to some level which has been assumed as 0. So usually in gravity, electrostatics, magnetism, or in general, such concepts, we take the potential energy of infinity as 0. We take when the system of charges is very, very far away. So just imagine these are our charges, this charge, this charge, this charge, this charge, etc. They are very, very far away. Think as if this is our universe over here. This is our universe. So let me call this as our universe. And they are so far away that almost at the boundaries of the universe. They are very, very far away from each other. So they hardly know that they exist. They hardly know that they exist because they are very far away. Kilometers is a understatement for them. So when they are infinitely far away, such a system will have a potential energy of 0. This is also called as your reference energy or reference potential energy. Reference potential energy. All the energies are always measured with respect to this situation, because when they are far away, they are not interacting with each other. They are not interacting, and because they are not interacting, they have no way to know who is there, who is not there. So because they are not interacting, they are not interacting with each other. That is why we have assumed the potential energy to be 0. So this is some important thing to be remembered. Reference energy at infinity is taken as 0. Now you bring these charges close enough to each other. Okay, now they are at some decent distances, maybe here, maybe here. Now they are separated by a finite amount. So now there is finite separation. Finite means one charge is, few meters from here, one charge is here. So now you can measure those distances. It is not infinitely far away. So finite separation is there. So for finite separation, this particular system which is there, this particular system which is there, this particular system which is there, it will definitely possess some energy. That potential energy is basically U. That potential energy is basically U. Now imagine these are all charges. All these blue dots were nothing but charges. They might attract, repel each other, whatever. So when I try to bring them together, there will be some repulsive attractive forces. So I might have to do some work. So in this process, when I'm going from here to here, in this process of assembling them, in this process of assembling the charges, when I am performing some work to bring them from infinite separation to some finite separation, whatever work I do completely gets stored in these charges, because now these charges might have some repulsive attractive forces. As soon as I leave that system, zoop, these charges will start moving because of the electro forces, Coulombian forces between them. So they are performing some work, they are moving, they are converting their stored energy into kinetic energies. Clearly it is like a stored energy in a spring. You take a spring and you compress it and leave it, zoop, it starts moving, it starts pushing things away. Or you pull it, it starts pulling those things, inwards. So this is exactly like that. These charges were chilling out at infinity. You assemble them, you did some work, whatever work you did got stored in the form of electrical potential energy. The moment you release them, zoop, they will start moving everywhere, and we know that the potential energy is getting used. Is that absolutely clear, everyone, till this particular point? Ajay, welcome. Okay, I'm so glad you guys are all excited. So I can say now that the potential energy is nothing but the integration of the total work done by that external force, total work done by that external force from infinity, this is very important, from infinity to that finite separation, to that basically finite separation, very, very important. So this is how you define the electrical potential energy. This is how This is the formula for calculating electrical potential energy. As simple as that. Everyone till this point absolutely clear? Everyone till this point absolutely clear, guys, how the formula is defined for electrical potential energy? The work done by the external force to assemble the charges from infinity to finite separation. By the way, you can always write this as negative of the work done by whom? Electrical forces, because electrical force will do exactly opposite work, just like explained before. If external force does 15 joules, gravitational was doing negative 15. Gravity was a conservative force. So electric force will do exact opposite. So to keep the balance of equality, it is exactly the work done by the electric force from infinite separation to that finite separation. This is very important why that minus sign came. Okay, exactly the same reason. Now keep this in mind. That yes, Sarvanan, you are a little bit late. Hi, Shriharan. Welcome, everyone. Now, please keep this in mind that electric force is a conservative force. Electric force and field is basically conservative in nature. And what is the meaning of conservative? I have already explained it right over here. The work done is not dependent on the path. And if you come back to the same point, the total work done will be basically zero. That is the meaning of conservative force and conservative field. Okay, sir, I understood now. So tell me, sir, what is this work which is done? What is this energy which is stored? Is there a value associated with it? Yes, definitely. I'll tell you. Sham, the JEE course link is there in the description box, which is the Sigma batch. And I would suggest don't join the Sigma batch today. I would suggest please join it tomorrow or day after tomorrow. Okay, tomorrow onwards you join, because I'm telling it openly, the price is going to drop tomorrow. Okay, and there is a reason for it, because there is going to be an entry point. Okay, so please join tomorrow. I don't want you to pay whatever some small discount it will be, but why do you want to spend that extra 300-400 rupees? Cool, fine, Sham. Okay, just wait for my announcement tomorrow. Now coming back to this concept of what is this energy stored. So let's say, for example, we just consider two charges. How many charges? Just two charges. And I want to calculate, okay, they are going to be separated, sir, by some distance. How much distance? Let's say R. This is the separation between them. Separation between the two charges. Separation between the two charges. Separation between the two charges. Which are those two charges? One is capital Q and the other one is small q. Eventually, the small q will come over here. So the manner in which we calculate the potential energy is simple. It is nothing but the integration of the work done by that external force from infinity. First it was at infinity, and slowly you bring it to a separation R. Slowly you are basically bringing it to a separation of R over here. So this work done is nothing but the force multiplied by the displacement. Force multiplied by the displacement. Displacement can be dr. Force is your Coulomb force, which is Q divided by, you can write dr or you can write dx also, and this is nothing but x square. So you integrate it with proper limits, and then you will get the potential energy for R separation. Potential energy for R separation, or you can just keep it as U only, one and the same thing. So that potential energy comes out as K Q Q divided by just R. K Q Q divided by just the separation between them. Q and Q are the charges, R is the separation between them. That comes out the formula after integration. Okay, this is the formula after integration. Remember that potential energy obviously is a scalar quantity. It is a scalar quantity, and also the units are same as that of work. So the SI unit of potential energy being joule and CGS unit being ergs. So this answer, whatever you get, will be in joules. It is a purely scalar quantity. But there is a simple understanding which you need to know, that if by chance, let's say for example, if you talk about both these charges, let's say both the charges are positive or both the charges are negative, or one charge is positive, other charge is negative. Okay, any of these combinations. These are the only combinations possible. So in the first combination, what you will see, in the first combination, that is when both the charges are identical signs versus both the charges are opposite in signs. You will see when both the charges are of the same sign, positive into positive, positive number, negative into negative is also positive number. So you will notice that our potential energy symbol will also be positive in this case. But if one is plus, one is minus, or one is negative, another is plus, then the answer will be negative in nature. Very, very important, guys. Keep this in mind. If any one of the charge is of opposite sign, then automatically the energy becomes negative. If both are of the same sign, only then the energy becomes positive. This also can be shown graphically like this. This also can be shown graphically like this, where you have potential energy on the y-axis and the separation between them on the x-axis. This is your 0, of course. So if both the charges are of the same sign, then the potential energy is going to be positive. Whereas if both the charges are of opposite sign, it will always be negative. So when it is negative, that means the forces are attractive in nature. The forces are attractive in nature. And when both are positive, they will repel each other. So the forces are repulsive in nature. You might have also seen that energy is negative whenever things are attractive, and whenever things are unstable, they are trying to go away from each other, the energy is positive. This is not just here, but also in chemistry, in many places in your chemical bonding and stuff, chapters like that, you might have seen such things. Okay, is that clear? All right. Sir, one doubt. I joined the Sigma batch now, and you posted the post in YouTube channel in any new course? No, any new course. It is just an entry point for the students who missed out the opportunity. So I will announce everything tomorrow. Okay. So new course will not come. It will be our Sigma batch, because we cannot make two best batches. Then they can't be best. It can have only one best batch, and the best batch for 2026 is the Sigma batch. Nothing else. Not just in Vedantu, but everywhere. Sigma batch is the batch. Okay, if you want a pure English batch. Okay, so whenever the forces are repulsive in nature, energy is positive. When they are attractive, it is negative. Is there a logical reasoning for it? I think so. Just think about it. I look at, in general, potential energy to follow this principle, where, see guys, whenever something has more potential energy, it will be basically sad, versus when something has low potential energy, it will be very, very happy. High, sorry, high potential energy. This is low potential energy. And everything tries to go from high potential energy to low potential energy. So many examples are there. Say, for example, I give you, imagine there is a object which is kept. There is an object which is kept on a table. This has high potential energy. Okay. What will it try to do? Eventually, it will try to come down. It wants to come down. Here it will be happy. Here it will be sad, because it is on the top. It wants to come down. It is being obstructed. Give a small push, zip, it will come down. So it is happy. Low potential energy. Okay. Another example which I can think of is your spring itself. Imagine the spring has been stretched like this. You are pulling it. Now it is unhappy. You release the spring, zoop, it will come back like this, and it is very, very happy. It is at its natural length now. It is at its natural length now. Not just that, imagine two charges which are separated by infinite separation. Two charges which are separated by infinite separation. Okay, there is lot of separation between them. Okay, and suddenly they become happy. If they are becoming happy, there can be only one reason when I bring them closer. Only when one of them is positive charge and another one is a negative charge, because they love each other. So they are becoming happy because they love each other. So that is why when the charges are opposite in nature and when they are closer, their potential energy is less. But we know for infinite separation, the potential energy was zero. The potential energy for infinite separation was zero. Hence, for finite separation, the potential energy must be lower than zero. What is lower than zero? A negative number. Getting my point, everyone? Similarly, if you have two charges which are positive in nature, two charges which are positive, or basically you can say like charges, this one is also positive, this one is also positive. Now, when they are really far away, they will be very, very happy. Yes, at infinite separation, they will be very, very happy and their energy is assumed to be zero. But when you bring them closer, that's when they will be unhappy. That's when they will be unhappy. And that's why that potential energy will become more than zero, which is positive. This example is a very good example of telling you what is the significance of negative versus positive potential energy. So two charges which are like, mean positive, positive, negative, negative, far away they are very happy, cool. But when you bring them closer, they don't like, they repel. So that's why their energy will increase and they will become unhappy. But the case is exact opposite for attractive forces. So when they are very far away, they are sad. So they come closer and their energy will reduce. So when they are far, the energy was zero. When they come close, energy will reduce lesser than zero. So what is that number lesser than zero? It is negative. Is that clear? Sujit, you can definitely watch, but provided your basic concepts of 11th are clear. Okay. Yes, JK the King, I am also there, but along with me, PNJ sir is there, who himself is an IITian and is teaching in our offline centers, and he's a fabulous teacher of physics. Okay, so I am also there, but you will have also PNJ sir for physics, and of course Diksha ma'am, Namrata ma'am are there. Along with them, you have Paul sir and other sirs and ma'ams for teaching chemistry and mathematics, because the subjects are huge, time is less, and bandwidth is also used. That's why we are taking two teachers per, or in chemistry maybe 3 teachers per subject. Okay, clear, Sujit? I hope I have answered all your doubts. Okay, so now that, sir, I understood what is the significance of the positiveness and negativeness of potential energy. Is there a way to calculate potential energy of a system of particles? Because if I have just two particles, I know this is the formula. And if I have to use, let's say, a question on this, maybe, yeah, maybe this one. Two charges are there whose values are given to me. Find the electric potential energy of that charged configuration. That is the question. This was a question in this year, JEE Mains 2025. So how do we solve it? See guys, the potential energy formula is Q divided by R. K value is 9 into 10 to the power 9. Charge 1 is 7 micro. Micro is 10 to the power negative 6. Next charge is negative 4 micro. That means again 10 to the power minus 6. But the distance, be careful guys, little bit. See, minus 7 and plus 7. So one charge is here, other charge is here. This is plus 7 centimeters. This is minus 7 centimeters. So what would be the total separation then? I think it should be 14 centimeters. Is that right? It should be nothing but 14 centimeters. Is that right? So yeah, let me put over here 14 centimeters. So 14 into 10 to the power minus 2. Do not do R square. R square will only come in your Force formula, correct. Yeah. Oh, I'm so glad, Sriharan, you are having a cheat code with you. You are cheating then, right? In a very good way, I'm saying that. Very good. Proud of you, my dear. Sriharan, you have watched all my playlists and concepts are clear. That means you are many steps ahead of your batchmates. And by the time you give JEE 2020, whatever, I think 9 or 8, whenever, you will, I'm pretty sure, do extremely well. Okay. So I hope you will come back then and you will comment over here or come in live chat and say, sir, I'm in this IIT in this branch very soon. I'll have to wait 4 or 5 years maybe. Okay. So do the math, guys, and see how much is the answer coming out to be. Yep. The answer 100% must be negative. We can also do a small cutting here and there, like 4, 2. This will become 7. This 7 and this 7 vanishes off. 2 9s are 18. So I'm getting 18. Now there is a thing over here. I don't have to solve the powers of 10. I mean, in the JEE exam. I'll tell you why. Because if you look at the options, there is only one option which says 1 8. Forget the decimal zeros, powers of 10. But whatever happens will be some power of 10. So 100% it has to be option D even without solving. But if there were two options which said 18, 1.8, 0.18, then I have no other option but to actually figure out what is that power of 10. Here clearly we can see this is minus 12. Minus 12 and minus 2 will become minus 10. So this will become basically 10 to the power negative 1. Hence the answer will be minus 1.8 joules, which is exactly our option D. Is that right? Very good. Excellent. So this was your JEE Mains 2025 question. Very laddu question, I would say. Now, sir, please tell me, what will you do if it is not just 2 charges, but let's say, sir, 3, 4, 5, 6 charges? Then what to do, sir? I'll tell you. There is a simple trick for it. If you have multiple charges, then what to do? Say, for example, you have a charge. Let's say you have a charge Q1 over here, Q2 over here, Q3 over here, and so on and so forth. Q4 over here, like that. What you do is try to figure out what is the potential energy between these two, then try to find between these two, then between these two, then between these two, then between these two, then between these two. Basically, all the combinations possible. So, whenever you have a system of charges, so the potential energy of the system is basically the sum of the electrical potential energies of all the pairs of charges, So it is basically sigma ij. What is I and J? I and J are numbers 1, 2, 2, 3, 3, 4, 5, 6, like that. They will all go from 1 to whatever number of charges are there. Maybe n charges are there. Here I have shown 4, but maybe total number of charges over here are n in number. So there will be even more combinations possible. Isn't that right, guys? Even more combinations possible here, there, everything. So many combinations are there. So, but just make sure I and J are never equal. You cannot have Q1, U11 or U22. It will be U12, U13, like that. Okay. But wherever I should not be equal to J. So the meaning of this is nothing but U12 plus U13 plus U14, like that, till U1n. All these things. So many things will be there. U23, U34. So many terms will be there, guys. Can you guess how many terms will be there? Can you guess how many terms will be there over here? The number of terms, how many number of such terms will come? How many number of terms will come? If you are a 12th standard student, you might have learned PNC. PNC, you would have learned, you should know the answer for this. Come on, guys. Come on, guys. If there are n number of points, and you are choosing two points at one at a time, and only you are looking at the combination, not at the permutation, because once first charge with the second charge energy is considered. You do not consider 2 with 1. That's it, once and for all. So it is basically n number of points, you are choosing 2 at a time. So NC2 number of terms will come. Correct. Very good, Salah Rama. So if there are 4 charges, 4C2, basically 6 terms will come. Okay. Understood, guys? How many terms will come? Perfect. So let's see a question on that, maybe somewhere. Yeah, this one. 3 particles, each having a charge of 10 microcoulombs, are placed on the corners of an equilateral triangle of side 10 centimeters. The electrical potential energy will be how much? Let's try to do this question. So, equilateral triangle, the side length is clearly mentioned as 10 centimeters, which is basically 0.1 meter. Then the charges are also given to me. What are the charges? All the charges are Q only, but the value of each charge is 10 microcoulomb. So 10 into 10 to the power minus 6 coulomb. Now, if you notice here, there are 3 charges. You will only have 3 combinations: U12, U23, and U31. That's it. This with this, this with this, this with this. If you count this with this is automatically counted. Don't do double counting. If 1 with 2 is done, 2 with 1 is automatically taken care of. They both have a combined energy. It's not 1 with respect to 2 or 2 with respect to 1. It's their total energy. So only 3 terms. Best part, all the 3 terms will be equal because of symmetry. So we are saved of tedious calculations. It will be K, Q divided by the side length. I can assume it as A, but it will be 3 times. And this is only because of the symmetry in the problem. Otherwise, it will be Q1, Q2 by A1, Q1, Q2 by A2, Q1, Q2, Q3 by whatever, A3. So many such terms might come. Okay. What is the value of K? It is 9 into 10 to the power 9, sir. What is the value of the charge? 10. Oh, 10 into 10 to the power minus 6 is basically 10 to the power negative 5, dear. So why not write 10 to the power negative 5? And again, another charge is also 10 to the power negative 5 divided by the side length, which is 0.1 meter, which is as good as saying 10 to the power minus 1 meter. So put over here 10 to the power minus 1. Come on, my dear students, what is the correct answer over here? Minus 5 and minus 5, minus 10. Minus 10 and minus 1 cancels, minus 9. 9 and minus 9 cancels, becomes 1 only. So the answer will be 9 joules. The answer will be 9 joules. Sorry. Oh, we forgot that 3. My bad. That's why that into 3 will be 27. My bad. So into 3 was there. So 9 into 3, which will become 27 joules. Which will become 27 joules, which is option A. Perfect. So into 3, because 3 terms were there like that. So this is how you solve the question of multiple charges potential energy. Okay. Awesome. Perfecto. Clearo. Let's go ahead. Maybe I have kept one more question, maybe. No, this is not that. No, that is potential. Sorry. We'll come to that after some time. Now, there comes another interesting concept over here. Observe this carefully. Many times they might ask you how much is the work done in a certain process. Very, very important. See, guys, maybe right now you have charge 1 here, charge 2 here, like that many charges are there. This is your nth charge. Right now it is in a particular configuration. Okay, this is configuration 1. This is configuration 1, or I would say initial configuration. Initial configuration. What you do now, you again rearrange these charges. Maybe Q1 you bring it here, maybe Q2 you bring it here, Q3 you take it here like this, and maybe Qn is over here. So you have changed the configuration. So this is basically your final configuration. Final configuration. You have changed the arrangement of the system. This is a process which was done. So you have changed it. or basically reconfigure it. Reconfigure it. Many such questions are there. You have just reconfigured it. In such a case, understand, you will be doing some external work. Whatever is the external work done, whatever is the external work done in reconfiguring it will be exactly the change in the potential energy, change in the potential energy, which will also be, the negative of the work done by the electrical forces. Negative of the work done by the electrical forces. Very important statement. And obviously, the change in the potential energy means I'm talking about final minus initial. What I'm talking about is final minus initial. This is very important. We have seen this thing at the start of the class itself, right over here. Where is it? See, I told you here only. Change in the energy is the work done by external force, but it is also negative of the work done by the conservative force. Here the conservative force is the electric force. So electric force is going to do the negative work, whereas the external force, whatever work it does, it goes in the potential energy changes. Very, very important. So let's see how can we use this in some question. How can we use this in some question? Say for example, I will give you, this is a very common question, guys. This is a very, very common question. There is a square, of side length A and 4 equal charges, of Q. If the side is, for example, tripled, if the side is basically tripled, find number one, the change in the potential energy, number two, work done by electrical force, number three, basically the work done by external force. All the three things you need to find. Okay, so let's try to do this question. First, let me draw it obviously. So the system will look something like this. Okay, there are our 4 charges. All of them are equal. All of them are equal. Q, 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 and Q. Okay, till this point, absolutely clear. Okay, the side length is given to be A. The side length is given to be A. I will also need this particular side length, I mean diagonal length, I would say, because this charge with this charge, this charge with this charge will also have potential energy. No doubt about it. It's a right angled triangle. So Pythagoras theorem can be used. If this is A, this is A, the diagonal length will be root 2 times of A. So each diagonal will be root 2 times of A. Is that absolutely clear? A square plus A square is 2A square. Take the root, it will become A root 2. I will need it for the calculation. So let's try to figure out what is the potential energy initially. There will be how many terms? 4 charges, 4C2 means 6 terms will be there. So calculate it properly. This guy with this guy, how much will be the potential energy? K, Q, Q divided by A. Same thing, this with this, this with this, and this with this. All the 4 terms will be equal. Getting my point? So that is why I will multiply it by 4. Basically, these are nothing but the for the charge pairs, on the 4 sides of the quadrilateral. On the 4 sides, this with this, this with this, this with this, and this with this. A is same, charges are also the same. There are also 2 diagonals, this with this, this with this. Distance and the charges are also same. So K, Q, Q, side length is nothing but root 2A. Like that, there are 2 diagonals. So this is for the charge pairs, on the 2 diagonals. As you can very easily see, K Q square by A is a common thing. And here you have the number 4. Here you have the number 4. And here you have 2 by root 2, which is exactly root 2. So this is what will come. KQ square by A, 4 plus root 2. Everyone till this point absolutely clear? Everyone? Yes, sir. Perfecto, sir. But that is not the end of the story. We want to find the change in the potential energy. So let's figure it out. How much is the final potential energy? Observe it carefully now. Say, if I talk about the final potential energy, the only difference will be this side length. And clearly, the side length is tripled. Only change will be A will become now 3A. That's all. So it will become K Q square. Instead of A, it will become 3A. And this thing will be as it is 4 plus root 2. Okay. What do I want to find? First thing, delta U. So delta U will be final minus initial. Okay, final is nothing but kq square by 3a, and this is 4 plus root 2 minus initial. Initial is this number, which is kq square by a, and you have 4 plus root 2. Just look at it, k except this 3, all the things are same. So this is 1 by 3 minus, if you forget this, it is just 1. Kq square by a in the bracket, if you assume this as some x, this is x by 3, this is minus x, that's all. So x by 3 minus x, so 1 by 3 minus 1, think of it like that, it will be negative 2 by 3. So this answer 100%, without doing too much of mathematics and opening the brackets, which is not needed, it will be negative 2 by 3 times k q square by a, and then you have 4 plus root 2 over here. So that is your change in the potential energy. Yes, it is basically going to be negative. What does this negative times tell you? What does this negative sign tell you? It tells me it is becoming happy because the change is negative. So it is more preferred. It is becoming happy. It wants to do it. Makes sense because these are four equal charges which repel each other. So when you increase their size, they are happy, they are relieved, they are away. They don't like each other, they repel. So that is why the energy had to come out, change had to come out negative. So it is perfectly fine. Okay. Now comes the next part. What about the external force work done? We all know external force work done is exactly the same as the change in the potential energy. So the work done by the external force will be exactly this only. So it will be negative 2 by 3 times kq square by a, and whatever is there over here, 4 plus root 2. No doubt. What about the work done by electric force? We all know work done by electric force negatively will be delta U. So if I shift that negative sign, we can all see negative will cancel, and it will be positive 2 by 3 kq square by A times 4 plus root 2. So the work done by the electrical forces between them is exactly this much. External force is this much and change in energy is this much. So all the three things we can calculate. So this is how you solve questions when multiple charges are there. These kind of questions are also very common in your JEE exam. Is that okay, everyone? Till this point? Currently, I doubt that BITS is better than NIT. Can I prepare for BITSET from now on or prepare from JEE and start preparing? Yes, Magnus, prepare for BITSET after first attempt. Nobody prepares for BITSET anywhere in India. Understand that. Everybody prepares for BITSET after JEE means first attempt. Okay? No one does that because JEE preparation is the mother of everything. It's the father or godfather, whatever you want to call. It's like the thing. When you prepare for JEE, you prepare for everything. Plus, you cannot depend on BITSET because BITSET has only like 2-3 campuses which you can prefer. And if you don't get, then you are doomed. So in JEE, okay, fine, you have IITs, you have NITs, your government funded technical institutes, so many private colleges which consider JEE main score. So the options are wider and it is wiser to prepare for JEE than for BITSET. Is that clear? Okay. Fine, sir. I understood what is electrical potential energy and how to calculate it for a system, sir. Very good. So now what the hell is this electrical potential now? What is this electrical potential that you are talking about? Okay. So let me explain. Imagine you have some system of charges. Okay, some system of charges. Some system of charges. And what happens is that if I actually put a charge over here, let's say Q, then this with this will have some electrical potential energy. It will have. It's like saying, if you all study, if you all Pandus and Champas study properly, then you will be in IIT. You have the ability to be in IIT. Agree or not? If there is a big if you work hard. But if you do not, all that is there is the ability. I can always say, if I don't clear IIT exam, sir, you know what? I had that ability, sir. I could have done it, but I didn't do it. Everybody can say that. So, is there an ability to get the energy? The another synonym for the word ability is the word potential. Do you have the potential to get into IIT? Similarly, these charges will ask themselves, do I have a potential, an ability, a scope of getting energy over here? How much is it? Positive, negative, like that. If there was a charge here. But then, how much is that potential? We cannot judge it with any other random charge. You need to have some specific charge as a standard. So what we do is we say like this, if there is a unit test positive charge, if there is a unit test positive charge, just like field is for the force, which is very specific per unit charge, same way electric potential is for potential energy, which is very specific, which is per unit charge. You can think of it like that. So what I will do is, I will say, okay, yes, you can do it. All you need to do is, let's say this is our boundary of the universe. Let's say this is the boundary of the universe. This is infinite. Okay. From infinity, you bring that test charge. You bring that test charge. Maybe I call it small q like this and place it over here. You bring that test charge and bring it over here. This is your test positive charge from infinity to that particular point. So external forces will be doing some work. Yes. So if it was the total work done by the external forces from infinity to that particular point, from infinity to that particular point, then it would have been potential energy. Then it would have been potential energy, which is U. But if I divide this with the charge which I am bringing, with the charge that I am bringing, okay, then what I will be getting is basically the potential. With the charge that I'm getting, then I'll be getting basically the electrical potential. As simple as that. So it's the same definition, but per unit charge. That's all. Yeah, everyone. So this is the symbol of electrical potential. So I will just block this off for all of you. These definitions are given in a very bad, crazy manner in your NCERT textbooks. If you open it, you will feel like, I don't know, like your head will spin, you will feel like sleeping or God knows what. Yeah. Is that clear? Is electric field never ends? Am I right? Yes, electric field ends at infinity. It's like saying it never ends. So it's a mathematical way. I say that it ends at infinity, but what is infinity? Never ending thing. So basically never ends. So again, this is a scalar quantity. It is a scalar quantity. And if you ask me the SI unit, it's very simple. On the top, you have joules. You have a joule. And at the bottom, you have a coulomb. Joule per coulomb is the unit. But there is a specific name for it. Just like when you accelerate 1 kg of mass with 1 meter per second square, then you call it as a Newton. So you generally do not write the unit of a potential in joules per coulomb. You call that as a volt. So a volt of potential is when you have to perform a joule of work. A volt of potential is when you have to perform a joule of work in bringing a test coulomb, 1 coulomb of charge, a test positive 1 coulomb of charge from infinity to that point, from infinity to that point. So that is basically your volts. Bear in mind that potential can be positive as well as negative. Yes, potential can be positive or negative because this work can be positive or negative. So there is nothing like potential has to be positive only because it's a scalar. So it can be positive, negative, or even zero at a point. Okay, so it can be positive, negative, or zero. There is no such thing that it has to be always positive volts. Okay, is this absolutely clear? What is the meaning of electrical potential? Okay, now think about it. If I go from infinity to that point and I measure that work done by that external force per unit charge, then the thing which I get over here is the word potential. But imagine I don't come from infinity. Maybe, just imagine I go from this point and I reach over here. This is my initial point. This is my initial point. This is my final location. I'm just taking the charge along this particular path from this point to this particular point. Then if I go from my initial point to my final point and I calculate the work, 100% it won't be the potential at that point. Rather, I'm going from a specific point to another specific point. So it will definitely not be the potential. What will it be then? 100% it will be the potential difference. So you might have heard about this word potential difference. This is exactly the definition. So instead of coming from infinity to that point, you go from one point to the another point, point 1 to point 2. That work done per unit charge is then the potential difference. That work done per unit charge from one point to the other point is then called as the electric potential difference. Electric potential difference. Electric potential difference. Very, very important. Is this absolutely clear? Okay. You solve ISA paper in single. This makes you good. Okay. Great. Sir, why you use test charge? Rama, remember electric field. Electric field did not depend on outside things. It was a property of a system of charges. Let's say I'm a charged body. I will say there is a field here around me. I have an aura around me. If you come here, I will apply a force. If you come here, I will apply a force. I'm warning everyone. It's like an aura. It's like my presence is being felt by everyone only if you place a charge. But even if you don't bring a charge, my aura is still there. I'm still saying my field is there around me. Same way, I'm saying there is a potential around me. Everywhere there is a ability to get potential energy. So I'm saying if you bring a coulomb of charge, this much voltage you will get, this much energy you will get. So if you bring double of that, triple of that, you automatically multiply by 2, 3, 4, whatever. So we keep a standard of a unit positive charge so that it's clear that per unit you are getting this much energy. If I bring 3 units, into 3. If I bring minus 5 units, into minus 5. That's all. Is that clear, everyone? All right, perfecto. Avinash, 100% is IIT only worth for engineering? Only IIT is worth? No. But is IIT worth? Yes. There is a difference in that. Because obviously you have very good engineers apart from IITs, and most of our ISRO scientists and people who send rockets and satellites in space are not IITians themselves. They are in fact from private engineering colleges. Okay. So it's not like only IITs are worth. But is IIT worth? In itself 100%. The tag itself is good, and you have a lot of prospects and things that you can not just brag about or claim respect for, but you can do in life. Okay, so that's the confidence, that's the power that you get once you have the IIT and tag. Okay, so electrical potential needs a test charge. Okay, for measuring it, which is Q, so that with the test I can get to know, yes, there is ability. It's like you can say, sir, you know what, I can crack IIT. Okay, fine, you give this test, we'll see. So you give a test and you score very good. Oh yes, you have the ability, you have the potential. But whether you crack it or not, that is another story. So ability is there. So for that, we need something to test. Now, is there a relation between the energy difference, potential energy difference, and the potential difference? The answer for that is yes, because this was per unit charge. Just think about it. If I bring this delta V, multiply it with this number Q, okay, what I will get over here is nothing but integration, the work done by that external force from this initial point to the final point. What do you think is this number on the right hand side? Come on, quickly answer in the chat box. Quickly answer in the chat box, guys. What do you think is that number? What do you think it represents exactly? Yes, it represents the work done from initial to the final point by external force. Means I am pumping some work, I am giving some work from bringing to here to here. That means I'm changing the energy of the system, potential energy of the system. So it's basically I am changing the electrical potential energy of the system. So this is also a very, very important formula. Q delta V is delta U. Q delta V is nothing but delta U. Very important. Is this absolutely clear? All right. Perfect. So this is, I know the total work done, but the total work done will be the change in the potential energy. So very important formula. Now that we know, okay, what is the meaning of potential difference and how to calculate this, please keep in mind all these places, that all of these are always independent. They are always independent of the path. They are always independent of the path which is being taken. Independent of the path which is being taken. So say for example, we do a question something like this. And I tell you that, hey, listen, that for a charge system and, or rather, the electrical force does minus 30 joules of work in moving a 2 coulomb charge. In moving a 2 coulomb charge. Question is, find number one, the change in the potential energy and the change in the electric potential. Find the change in the potential energy and also the change in the electric potential. That is the question. Okay, let's see if you guys can figure this out. It's not very difficult. You can definitely get this. You definitely can get this. Think about it. How would we do it? Why is it path independent? Remember, I had told you before only that, where is it? Conservative forces, the work done does not depend on the path, and electric force is the conservative force. It does not depend, the work does not depend on the path. Hence, when I integrate this, when I integrate from initial to final, no matter which path I take, it is always going to be the same. So even if I choose some another path over here like this, still the work done would be definitely the same. It will not at all depend on the path. Is that clear? It is a conservative force. All right. So let's see if you guys can figure out this question. First of all, it is clearly mentioned over here that the electric force does negative 30 joules of work. We all know work done by electric force, which is conservative force. The negative of it is delta U. and electric force itself has done minus 30 joules. So therefore, what should be the value of the change in the potential energy? It should be positive 30 joules. It should be positive 30 joules. Everyone till this point absolutely clear? Okay, sir. So now what is the change in the potential? We know delta U is Q delta V. Delta U is 30. The charge that you have moved is 2 coulomb. So we can figure out what is the change in the potential. 30 by 2, which is basically 15 joules per coulomb, which is nothing but 15 volts. So there is a voltage difference of how many volts? 15 volts. There is a voltage difference of 15 volts. Is that absolutely clear? Okay, that is how you solve this particular question. Let's do more questions so that you guys get a hang of it. Going to one more question coming up on your screen. Here it is. Say for example, that is fine. Yeah. Say for example, an electron is moved from point 1 who has a voltage of plus 20 volts to point 2 whose voltage is negative 20 volts. Question is, find the change in the potential energy and what is the work done by the external force in this case. What is the work done by the external force in this case? An electron is moved from this point to this point whose voltages are given. What is the change in the energy and the work done in this case? Think about it. Because we want to figure out the change in the potential energy, which is the charge multiplied by the potential difference. The charge of an electron is basically E only. Potential difference means V2 minus V1, final minus initial. What is the charge? 1.6, 10 to the power negative 19. Final potential minus 20. And be careful, the charge of an electron is actually negative. Yeah, be careful, it is negative 1.6. So we need to be aware of that. Minus initial voltage, which is plus 20. So is this absolutely clear? Minus 20 minus 20. This is plus positive voltage. This one was negative voltage. So what will happen, guys? This will be negative 1.6 into 10 to the power minus 19 coulombs. Minus minus will again become minus 40 only. Yeah, that's what you will get. Minus minus over here will become positive. So 16 fours are, how much is it? It is nothing but 64. So 1.6 into 4 will become 6.4, but that 0 is there. So 64 into 10 to the power minus 19 joules. So that is the change in the potential energy, which also is the work done by the external force. So 64 into 10 to the power minus 19. Yes, very good, Rama. Inaya. JK the King, I'm right now in Bengaluru. Yeah, my studio is in Bengaluru. Right, perfect. Great. Is this clear how to solve these kind of questions now? So whenever charge voltages are given, you can find energy change, or from energy change, you can find voltage difference, one and the same thing. Cool. There are some interesting questions though, sometimes given like this. It is mentioned, for example, a charge of, let's say, 2 coulombs is accelerated by a potential difference of 6.4 kilovolts, and the mass of that charge is given to be, let's say, 8 grams, or let's say we say it is 0.8 gram. That is given to me. Question is, can you find the kinetic energy gained also the final speed. Also the final speed. This is the question. These kind of questions also come very much in modern physics as a part of a bigger problem. It is not a problem in itself, but a part of a big problem. So it will be a step. So how to solve this? Let's understand it. Imagine you have a charge over here, Q. Okay. Right now, this charge is at rest. What happens is that you accelerate it, and it finally gets some speed. That same charge will get some speed over here. So I'm accelerating it by some voltage and it is getting some speed. Now, what exactly might be happening? Understand. Over here, the kinetic energy initially is zero. But over here, the kinetic energy finally is there. So where did this kinetic energy come from magically? It can only come from one place. If you remember work power energy chapter, the loss of potential energy. Exactly. So what should be happening is there must be in this process, a loss of electrical potential energy, which causes the gain of kinetic energy, which causes the gain of the kinetic energy finally. Is this clear? Because energy has to be conserved. All of this I'm able to tell on what basis? The conservation of mechanical energy. Conservation of mechanical energy. Oh, okay, sir, got it. So you are telling me that whatever this kinetic energy has come, it has come only because of the loss of the energy. So there is some potential energy which has been lost. But sir, I know what is the potential energy loss, sir. Oh, is it? What is that answer? I just know that formula. That formula is charge into delta V. The potential energy changes charge into delta V. So why not use that over here? That is my thing. So why not write it as charge into the voltage difference? Perfect. So what is the charge? It is clearly mentioned as 2 coulombs. What is the voltage difference? 6.4 kilovolts. So into 10 to the power 3. Now 6.4 into 2 is 64 to the 128. So this will become 12.8 into 10 to the power 3 joules, which you can also write it as 12.8 kilojoules. So that is the final kinetic energy of the charged particle. Is this clear? How do we solve it? Everybody with me understood how to solve this particular question? Okay, sir. Now, that is not the only question. Another question is, what is the speed of it? Well, that also we can solve. From here only, if you notice, kinetic energy would have been actually half into m into speed square. So that would have been charge into the voltage difference. So keeping charge into voltage difference on the top and bringing this number 2 over here and bringing the mass downstairs, that would be V square. So V will be root of all these things. V will be 2 times Q delta V by mass, right? So therefore, how much should it be? Let's try it out. So maybe over here only we can figure it out. So that will be equal to root of, okay, 2 into the charge. Charge is how much? Charge is how much? 2 coulomb. Okay, voltage difference is 6.4 kilovolts. So 6.4 into 10 to the power 3. The whole thing divided by the mass. Mass is 0.8 gram. So 0.8 multiplied by 10 to the power negative 3. Yeah, in kgs. 0.8 into negative 3. Okay, so what will happen is this 2 and 2 will cancel, or okay, I will do it step by step only, not a big deal. We'll do it step by step. So 2 and 2 will come outside. It will become just the number 2. Okay. 6.4, I can write it as 64 into 10 to the power 2. Nothing wrong in that. Deliberately, I did it because I know 64 is a perfect square. Then over here, if I may, I can write it as 2 into 4. 8 is 2 into 4, and this decimal was there. So 10 to the power minus 4. Okay, perfect. 64 by 4, we all know is nothing but 16. So this will become 16. Root of 16 is basically 4. So 2, root of 16 is 4. And inside the root, what is there? Let's think carefully. This minus 4 will go on the top and it will become plus 6. 2 plus 4 is basically 6. Root of 10 raised to 6. Root of 10 raised to 6 will remain. And below this 2 is remaining. So this will be nothing but 2 fours are 8 by root 2. 10 to the power 6 is nothing but 10 to the power 3 when you take the root. This much meters per second is the answer. 8 by root 2 into 10 to the power 3. Is that clear, everyone? Yeah. ISC requires very high closing. Rama, I'll be making a separate video very soon regarding the closing and opening ranks. In fact, okay, right. Perfect. So, sir, now I understood what is the meaning of electric potential. What is electric potential? It is just like field for force per unit charge. If you measure the energy, it is basically electric potential. It is a scalar quantity. It can be positive, negative, and if you multiply it by the charge, you get the energy of that system. But sir, is there a formula for finding electric potential due to a point charge? Yes, electric potential due to a point charge. Due to a point charge. Imagine there is a charge capital Q over here, and at certain distance r, I'm interested in figuring out what is the potential. So in order to find that potential at this place, if you use this formula, integral the work done by the external force from infinity to that particular point, which is basically at a distance r, and you divide it by the test charge. Okay, the answer that you get over here is just k, and then you have this actual charge, the whole thing divided by r. K capital Q divided by r. Instead of KQQ, it is just KQ by R. That's it. This answer is in volts. This answer is in volts. So this is the potential due to a point charge. Potential due to a point charge. Is this absolutely clear? Yeah? Everyone? Till this point? Absolutely clear? Very good. So now, if you draw the graph of, let's say, potential versus distance, if you draw the graph of potential versus the distance, how will it look like? Yeah. So also root 32, yes, Inaya, yes, definitely you can do it, my dear. Definitely. If you draw the graph, imagine the charge is positive. Imagine this charge is positive, then the potential will also be positive always for a positive charge. But if the potential is measured for a negative charge, all the values will be negative. So keep that in mind. So everything will be negative. This is for a negative charge. Is this absolutely clear? Everyone, for a negative charge, everywhere it will be negative. Okay, very good. Like I said, Rama, actual meaning of potential is, by definition, if you go, it's the work done to, if I say, I'm a charged body. I want to see what is my potential here. If I bring a charge from infinity to this point, I will do some work. So divided by the charge, whatever is the answer, the joules per coulomb is the potential. But like the other meaning, forget the textbook meaning. I said potential is the ability to gain energy if I place something over there. So I am a charged body. I say, do I have potential here? Means, do I have the ability, the capability of gaining energy if something is placed here? I say yes. I'm like, how much? 10 volts. 10 volts meaning 10 joules per coulomb. So if you place 1 coulomb, then you will get 10 joules. If you place 2 coulombs, you will get 20 joules. That is the meaning of potential. Okay, do I have the ability? Okay, so potential is not energy. Potential is the ability to gain energy. Potential energy is the actual energy which is stored. There is a difference. Getting ability versus actually having. You, Anaya, you have the potential to get into IIT. But when I'm putting the charge, it means like when you actually place a charge means you are actually working hard and then you get that energy. Okay. So when you work hard, you actually get that energy. Is that right? K is a constant, Coulomb's constant, Sravana. Yeah. Perfect. Which we have told before, 1 by 4 pi epsilon naught, 9 into 10 to the power 9. Chapter 1, lecture 1. Yeah. Few days back only I have done it. Okay. Now, sir, this is the potential due to a point charge. Do I have a question on that alone? Maybe no. Sorry. So what if, sir, there are multiple charges? Then what to do, sir? It is just like before, guys. Imagine there is a charge 1, there is a charge 1, there is a charge 2, charge 3, charge 4, like that. N charges are there. N number of charges are there. And I am interested at this point, what is the potential? All I will do is use superpositioning, find potential due to this, 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 and add them up. So I will say at this particular point, which might be at a distance of R1, R2, like that, Rn. So the net potential at any particular point is nothing but the scalar sum of all the potentials due to all the charges around. And this principle is obviously called as superpositioning principle. Superpositioning principle. Superpositioning principle. So the net potential at any point is nothing but V1 plus V2, like that till Vn, and undoubtedly V1 is nothing but K Q1 by R1, V2 is nothing but K Q2 by R2, like that you do K Qn divided by Rn. So K will be common, and if you want, you can do the rest of the maths. So this is what the potential will be. It is a scalar sum because potential in itself is a scalar quantity. Potential in itself is a scalar quantity. Is that absolutely clear? How to find the net potential due to all the charges? Okay. Okay. Inaya, you love mathematics. Then definitely you should please try for the Chennai Mathematical Institute and even ISI, Kolkata. Please try it. Last year we had ISI All India rank 1, and we had, I think, some 3-4 students in top 10 rank in ISI exam and many others in the top 100. If you are really interested, then I would suggest you to get yourself trained by our Olympiad team. There is a separate Olympiad batch. If you want, I'll make a separate video on that. Okay, so you can search for it also. But you know that, or just comment below. I will share the Olympiad batch. It's a beautiful batch, specifically meant for those students who want to get into astronomy Olympiad or maths Olympiad, or get into ISI, CMI, and all these kind of institutes. Okay, so very targeted niche batch. Superpositioning, Raju. Oh my God. Am I audible now? Am I audible now? Am I audible now? Am I audible now? Okay. So I was just saying that over here at this particular point, imagine there is a champa and there are these charges which are pandus. A pandu meets that champa and says, "Hey, I love you." Another pandu says, "Hey, champa, I love you." These pandus discover that, hey, there are other pandus also who love the champa. Oh my God, now we'll love champa less or more. No, you'll still love champa the same as before. They will not be affected by other pandus. This is called superpositioning. Every pandu who meets champa is saying, "I love champa, I love champa." So champa is getting all the love collectively together, and it is not dependent on other Pandu's love or affection. Got it? So every charge is giving some potential, and their total potential is just the sum, as if the other charges are not even there. It is their story. This charge will say, "I'm going to give you this potential, boss. I don't care about other charges." Every charge is superpositioning onto or all the other potentials to give the total potential. Is that clear, everyone? All clear? Awesome, awesome. So that is basically your superpositioning principle. Let us try out some questions coming up on your screen. Here it is. As shown in the diagram, charges Q and minus Q are placed at the vertices of B and C of isosceles triangle. The potential at vertex A. Very laddu question. Everybody spam the answer in the chat box. Everybody spam the answer in the chat box, my dears. Yes, this positive charge, let's say this is distance R. Obviously, this is also R. At this point, you want to find the potential. It will be K Q by R plus K negative Q by R. That is a negative Q charge. What will happen? It will just become 0. Hence, the answer should be a big fat 0. B option for IIT Bombay. Very good, Salah. Yes, they cancel each other in a correct. Perfecto. Amazing. Yeah. So that's how potentials work. That's how potentials work. Let's see another question coming up on your screen. Infinite charges are there. If you remember, this kind of question, we did it in the electric field lecture, electric field part. There were many charges, and due to every charge, there was basically, if you go back here, it was there in the electric field class. Where is it? Over here. We did it somewhere, maybe. Every charge gave some electric field. What was the net electric field due to all the charges? My internet has gone slow. It's okay. Never mind. And what is the net electric field? So same thing over here. This question also is like a series question. I want you to try it out as a homework, because if you attended the previous class, you know this also. So this is your homework question. Answer is there on the next slide. I'm not going to show you. Okay. Answer in the comments. I want to see all your answer in the comment section. Cool, guys? Everyone will be able to do it. It's not that difficult. Just think, okay, this is origin, this is 0.1, this is 0.2, this is 3 centimeters, this is 4 centimeters, and infinite charges are placed. Each of charge Q, 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 Q. Add them up, you will get the answer. You will get the answer. V1 plus V2, like that. Infinite terms will be there. It's a GP series most likely. Something like that might be there, and you will definitely get the answer. Okay, let's do another question coming up on your screen. A regular hexagon of side 0.1 meter has a charge 5 microcoulomb on each of its side. Calculate the potential at the center. How much is the potential at the center? Well, I can see whatever is the side length will also be this length from here to here, and every side will be the same, every length is the same. So the potential at point O will be KQ by R, but it will be 6 times. 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. 6 times it will come. That's all. K is nothing but 9 into 10 to the power 9. Charge is 5 micro, so 5 into 10 to the power negative 6, and into 6, the whole thing divided by R. R is 0.1 over here. Okay, so what is it? 6 5s are 30, so 9 into 6 5s are basically 30, and this is 9 and minus 6, so it will become 10 to the power 3. This is 0.1, so 10 to the power minus 1. 9 threes are 27, so 270 into 10 to the power 4. So it will become 27 into 10 to the power 5. What is it? Volts. 27 into 5 volts. So that is the answer to this particular question. So I think they have made a mistake in that point over there. So it should be 2.7. So it should be not 2.6. It should be 2.7 into 10 to the power 6 volts. Definitely that is the answer. Everyone clear about this? How to find it out? Directions don't matter. Please understand, if it was the question on the electric field, then the answer will be 0, because this guy's field and this guy's field vectorially will cancel. These two will cancel. These two will cancel. So field is a vector. So direction matters. But potential is a scalar. So just add them. Don't worry about the direction. But if something has a sign, take that into account. Okay? I hope this is absolutely clear. Now, let's come to the final concept of potentials, potential surfaces, and how they are related to fields. See, remember, field lines used to point in the direction of where the force is going throughout that space due to a charge. Equipotential lines, like the name suggests, it connects. It basically is an imaginary thing. It connects all the points of same potential. It's going to connect all the points of the same potential. It's an imaginary surface. It is not a real thing. It is not a real line. It is an imaginary thing. All the points of the same voltage or potential connected together. It's an equipotential surface, equipotential line, or volume, whatever you want to say. So, say for example, I give you a positive charge versus a negative charge. Which are those points with the same potential? Okay, let's try to figure that out. Which are those points with the same potential? As you can see over here, all the points on this particular circle have the same potential, because same distance, direction doesn't matter, same distance. It's a concentric circle. If I go slightly far away, I think the potential will reduce a little bit. If I go slightly far away, the potential will reduce a little bit. And all these points are now at a newer potential around that circle. If I go more far away, then it will be even less. If I go even more far away, it will be even less. So it will keep on reducing. It will keep on reducing the potential as I go far and far away. This is how it will look like. Is that absolutely clear? So these are all equipotential surfaces. Similarly, for a negative charge, be careful. Negative sign matters. As you come close, the potential will increase. Yeah, be careful. Sorry, it will decrease, my bad. As you come closer, it will decrease. And I'll tell you with this graph also, which I have given to you just some time back. Where is it? Second, this and all is not needed. This particular graph. If you take a positive charge, as you come close, the potential will increase. But for a negative charge, as you come close, the potential will decrease, guys. Yeah, as you come close, the potential will decrease in the value. So be careful about it. So as you come close for negative charges, the potential value will be lesser and lesser. So here it is very less. As you go slightly far away, then the potential slowly starts increasing. Okay, it keeps on increasing as you go farther and farther away. Okay, so that is how it looks like. So for a positive charge, the potential increases as you come close, but for a negative charge, as you come close, the potential value keeps decreasing. So these are all your equipotential surfaces. So can I say that for point charges, for point charges, for point charges, the equipotential surfaces are concentric spheres, are basically concentric spheres, one sphere inside the other. They are nothing but concentric spheres. Okay, I hope this is absolutely clear. Very good. Now, an interesting thing to notice regarding equipotential surfaces versus the electric field lines is that if you put both the diagrams onto each other, see, these lines show electric fields, these dotted lines show equipotential surfaces. Can you notice one trend? Can you notice something very unique? The straight lines, radial lines are electric fields. The red ones are the equipotential surfaces. Yes, you might have guessed it by now that if there is an equipotential surface, if this is an equipotential surface, maybe like this, maybe like this, these are all equipotential surfaces, you will always see the electric field lines are perpendicular to it. Yes, always you will see that the electric field lines at every single place, they will be perpendicular to it. They will be perpendicular to it. Very, very important. Everywhere. Not just that. Observe one more thing. Electric field will always go towards the lower potential. Makes sense. Look at this diagram. This is so higher potential, lowest potential. Due to positive charge, electric field lines go outwards. But due to negative charge, the electric field lines come inwards, high to low. So always this is true. So electric field lines, these are our field lines. So this is our electric field lines. You will notice that they always go from high voltage to low voltage. So maybe this is a higher potential and maybe this is a lower potential. Very, very important. So two important things which you are learning: equipotential surfaces are going to be what? Perpendicular to field lines. Is perpendicular to the field lines. Next important thing, if you have high potential versus low potential, electric field always goes from, the field will always travel from high voltage to the low voltage, from high voltage to the lower voltage. Very, very important. These are two important properties. Another live example of this is when you have uniform electric field. Remember uniform electric field? So when you have uniform field, when you have uniform field, remember the field was constant. The field vector was nothing but constant in magnitude and direction. It was going like this, constant. Equipotential surfaces are just parallel planes. This is an equipotential plane. This is an equipotential plane. This is an equipotential plane. As simple as that. Okay? Very, very easy. So parallel lines are the fields. So perpendicular to that will be the equipotential planes, one after the other. One after the other. Very interesting thing to see. Now, going ahead, say guys, say for example, if I tell you that listen, there is a equipotential line like this. There is a equipotential lines like this. Maybe this is minus 30 volts, minus 20 volts, minus 10 volts, and maybe I have a charge over here of minus 3 coulombs, and I get it over here. I am moving this charge along this path. Can you quickly tell me in this particular example, how much is the change in the potential energy? How much is the work done by electric force? How much is the work done by electric force in this particular example? Well, if you notice over here, I'm taking the charge from one place, one potential to the other potential. So there is a potential difference. So there will be potential energy difference. So we know the formula for it. The potential energy difference is charge into voltage difference. The charge you are taking is -3 coulombs. Potential difference, final minus initial. Please remember, this is final, this is initial. So final voltage is basically -30. So minus 10 volts. Okay, so this will become -3 multiplied by -30 plus 10, -30 plus 10, which is as good as saying -20. Minus is positive, 3 2s are 6, so 60 joules. So the change in the potential energy is 60 joules. Perfect. Yeah, perfect. All right. How they form equipotential surfaces, Rama? Which one are you saying? This one? This is some random example if you are talking about the previous one. Because if you draw perpendicular to parallel lines, what will it be? It will be a plane. So all the points on this plane will be at the same voltage. The electric field will always grow from high to low potential. So this will be another potential, but it will be lower. This will be even lower, another lower. So as you go forward, the potentials will keep on getting lower and lower. Is that clear now, Rama? All right. So talking about the next part, what is the work done by the electric force? Electric force negative work is delta U. That was standard formula. So negative of that electric force ka work is 60 joules. So electric force has done a negative 60 joules of work. So that is the answer for the second question. So with these diagrams, you can easily solve these kind of questions as well. So maybe we can take up an example over here. Oh, how will the equipotential surfaces look like for two positive charges? We know how the fields look like. If you know how the fields look like, draw perpendiculars to it. That's it. That's it, guys. So we know due to two positive charges, how do the field lines look like? The field lines, I'll just show it vaguely. It will look something like this, isn't it? Due to the positive charges. Now you just need to draw the equipotential surfaces. So probably one perpendicular every point here, then another perpendicular every point over here. Then over here, you cannot probably draw those perpendiculars so easily. And when you come over here, probably it becomes like this. Look at that. That is how it will look like. Yeah. So this is probably how it will look like. Yes, it is exactly like that. So these are your equipotential surfaces. If you know the field lines, drawing a perpendicular very easily can give you the equipotential surfaces. Clear? Hi Radha. Hi Hemant. Hi Nagraju. Very good. Perfecto. Perfecto. Very good. Sir, which IITs are good for computer science? Avinash, all the IITs are good, but usually people choose IIT Bombay. Okay. Let's see if you can do this particular question, guys. Okay. Figure shows some equipotential lines in some space and an object is moved from A to B, A to B, A to B. Then the question is the work done is least or highest or equal in which of the following? Okay, work done is more in one, work done in two is the least, work done is same, or the work done is three is more than two but equal to that in one. Okay, look at it. Same charge is moved from one point to the other. Guys, we know that if the question is on the external work done, it is a question of change in the energy, which is charge multiplied by voltage difference, which is as good as saying charge into from A to B, right? So final minus initial voltage. So basically compare VB minus VA. Just compare VB minus VA. If you do VB minus VA over here, it will be 40 minus 20, which is basically 20. VB minus VA. VB is probably this is 10, 20, 30, 40 minus again 20, which is again 20. Oh my God, great. This is 20. This is 40. Oh, this is also 40 minus 20, which is again 20. So everywhere this is 20 volts. This is the same. So what can you say about the external work done? It is also going to be the same. Everyone till this point, absolutely clear? The work done is basically the same in all the three diagrams. Very, very straightforward. Perfecto, perfecto, perfecto. Amazing. Now let's come to the place where we discuss how field and potentials are related to each other. How fields and potentials. This is the last part of today's class. See, I'll tell you what. One thing is there that electric field is perpendicular to the potential surfaces, as told before. But also remember one thing. Say, for example, the field is very strong and then it becomes weak. The field is very strong and it becomes weak over here. There is a weak field versus a strong field. Wherever the field is strong, you will notice one thing, that the equipotential lines are very close to each other, and as you go far away, I mean where the field is weak, the spacing between them reduces. Meaning here the potential changes quickly. The potential changes faster, or rather quickly, I can say. Here the changes are gradual. The changes are gradual where the field is. So we get a new term called as the potential gradient. Potential gradient. This term, potential gradient, is nothing but the rate of change of potential. This potential gradient is nothing but how quickly the potential changes. So rate of the change of the potential, rate of the change of potential with respect to basically the distance which you have traveled. Obviously, the potential will change quickly where the field is strong, meaning E is more. This term will be small where the field is weak, that means E is less. So it is exactly going to be like this. dV by dr will be equal to, if E is more, this is more. If this is less, then E field is also less. But it always comes with a negative sign. This is something which you should be careful about. dV by dr is a negative E. Why does this negative sign come? Why is this negative sign coming? This negative sign symbolizes that the field is towards the lowered potential energy, is towards the lower potential. That is what it is symbolizing. So if I go from one place to another and I find the potential is increasing, then the field is opposite to that. That's another way of looking at it. So if I go from one place to another and I find potential increase, field will say, no boss, I will always go from high to low, not from low to high. So that negative symbolizes the direction of the field is always towards the lesser potential, is always towards the lesser potential. So this is a very important formula. If you ask me what is the derivation for it, it comes from this. I mean, the small work done is negative, this is by the electric force, is negative of the change in the potential energy, and this is nothing but the electric force into displacement, which is dr, is nothing but minus du. So if I take this electric force and divide it with the charge, and if I take the potential energy and divide it with the charge, this potential energy per unit charge is nothing but potential. This is nothing but displacement. This is nothing but the field. So I will get field is negative dV by dr. So this is the simple derivation of it in case you are interested. Okay, very, very easy. And both sides I have divided by the charge. So force by field, force by charge is field. Energy by charge is potential. That's all. That's the only thing. So that's how you get the answer. Is this absolutely clear, my dear students? Perfect. But be also aware of one thing. Be also aware of one thing. When I do this, understand technically speaking, it's a vector quantity. This is a vector, this is a vector, this is a vector, this is a vector. This was a dot product. This was a dot product. So technically there was a dot product here. So by chance, if I integrate it, meaning something like this, dv will be negative of e dr, e dot dr. If I integrate it, meaning like this, integral dv will be integral of e dot producted with dr. So when you integrate, be careful, there is a dot product. Meaning when you write it like this, it's fine, no problem. But when you take this dr over here, it is actually e dot product with the displacement vector. Okay, there is a dot product when you shift that dr on the top. That is something which you should be aware of, because it comes from the concept of work, guys. Work is the dot product of force and displacement. So if you maintain those things, there is always a dot product over there. Okay, perfect. Let's do some questions on this then. Let's do some questions on this. Let's go down. Say for example, we are going to look at this particular thing. The field E vector is given by minus x square, or let's say minus 4x square I cap Newton per coulomb, and the potential at origin is 10 volts. Question is, find the potential as a function of x and the potential difference between x equals to 2 and x equals to 1. X equals to 1. That is the question. This kind of questions are also very common in JEE. So let's try to solve this. The field at a point is minus 4x square I cap Newton per coulomb, and the potential at the origin is given to be 10 volts. Find the voltage as a function of x. Okay. Field is given, potential is asked. Field is given, potential is asked. This is the formula I will use. Field is given and potential is asked. So this is the formula that I have to use. So let me write it down over here as it is. So integral of dv is negative e dot dr. Okay. Now, if you notice over here, our electric field is nothing but minus 4x square I cap. And since the electric field is only in the x direction, there is nothing to move in the y direction. So why will you even break your head in moving in the y direction? Everything is in the x axis. So I will move by a dx amount in the I cap direction and put a dot symbol over here. So this will become minus minus is plus, 4 will come outside. It will I cap into I cap is 1. So it will just become x square dx. And over here, I will just be left with integral dv. Is this absolutely clear, guys, what we have just done? Negative negative is positive, 4 comes outside because it's a pure number, x square into dx, I cap into I cap is 1. Okay, so this is how you solve this integral. Now we will put the proper limits. For the limits part, we will see this. At the origin, the voltage is 10 volts. So when x is 0, origin, the voltage is 10. But at x, what is the voltage? So these will be the limits of the integration. Getting my point? It should be corresponding. This was given to me. At origin, the voltage was 10. At x, what is the voltage? So origin, this voltage. At x, what is the voltage? So let's see. Integration of dv is v only. So v will be the integral. Put v and 10 over here, upper and lower limit. 4 is as it is. X square's integration is x cube by 3. Is nothing but x cube divided by 3. I'll put 0 over here and x over here. Let's see what happens after the integration. You will put first v, and then you will put 10 and minus over here, then put x and then put 0. So 4 into x cube by 3 minus 0 cube by 3, of course. So therefore, v will be equal to, this 10 will go over here, 10 plus 4 by 3 times of x cube volts. This is the answer to this. This is the answer to the first part of the question. This is the answer to the first part of the question. Is this absolutely clear? Now let's go to the next part. What is the potential difference is asked. Okay, so what is the potential at x is equal to 1? Let's substitute 10 multiplied by 4 by 3. Instead of x, I'll put 1 cube. Similarly, what is the voltage at x is equal to 2? So 10 plus, it should be, my bad, 10 plus. So 10 plus 4 by 3. Here I'll put 2 cube. Now the question is really on the potential difference. So delta V, that is what is asked, will be V2 minus V1. So V2 minus V1. So it will be 10 plus 4 by 3, 2 cube minus 10 plus 4 by 3 into 1 cube. 10 will cancel. 4 by 3 is common. So it will be 2 cube minus 1 cube. What is 2 cube, guys? What is 2 cube? It is 8. Minus 1 cube is 1. So it will be 4 into 7 by 3. 4 into 7 is 28. So it will be 28 by 3 volts. So the answer is 28 by 3 volts. Very good, everyone. Absolutely clear how to solve these kind of questions on integration wherever this kind of formula is involved. This is very rare, but still I have given it to you how to solve in case it comes. But sir, will question come from this formula, sir? E is equal to dV by dr. E is equal to dV by dr. This formula, will it be used? Actually, most of the times this question only comes. Usually, you will see most of the times this question only will come. For example, say the question says the potential V as a function of x is, let's say, 5 log x. Question is find the field. Question is find the field. That kind of question. Okay. So let's see how do we do it. As you can see that whenever potential is given and field is asked, field is minus dV by dr. Here everything is in x. So why not instead of r put as x? So it will be minus d by dx of potential, which is 5 log of x. 5 log of x. So minus 5 will come outside and derivative of log of x. What is it? It is 1 by x. So the answer will be minus 5 by x. Minus 5 by x. That's it. Minus 5 by x Newton per coulomb. Minus 5 by x Newton per coulomb is the answer. You tell me x, I'll tell you the field. It's a non-uniform field. Very, very easy. Very, very easy. Isn't it? But sir, is it necessary it will be only in x equation? What if it is in x and y or something like that? Those kind of questions also can be solved. I'll tell you how. For example, the voltage is 7xy plus y square. Chumma, I have taken some random thing. Question is find the field. Find the field. What to do in such scenarios? Observe carefully. Observe carefully. X and y both are there. Both are there. Now what to do in such cases? You write separate formulas for x and y. For example, electric field in x will be rate of change of voltage with respect to x only. So when you write it like this, minus d by dx 7xy plus y square, I am differentiating it with respect to x. Everything else becomes constant, meaning minus 7y is a constant, and I'm just left with dx by dx plus, sorry, not plus, minus, oh, y square is a constant only, guys. So d by dx of a y square. So basically y square will come outside, and d by dx, what will be remaining? 1. Okay, so this is minus 7y into 1 minus, this is y square, constant's derivative is 0. So this answer will be minus 7y. So electric field along x-axis will be minus 7y. Everything else apart from x is a constant. Treat it like that and solve it. Same way, when you try to find EY, electric field in y-axis, take the derivative of the voltage with respect to y. So it will be minus d by dy of this whole thing 7xy plus y square. Okay, separate out the terms. Everything apart from y is a constant. So minus 7x is a constant. So dy by dy. Here y square variable will come as it is. So it is not a constant. Except y, everything is a constant. Okay. So this will become minus 7x dy by dy is 1 minus 2y. So it is basically minus 7x minus 2y. So that is the y component. That is the y component. Now, if you want to find the total vector, what will it be? It will be ex I cap plus ey j cap. Ex I cap plus ex j cap. So what is ex? This guy. So it will be nothing but minus 7y. What is ey? Just start putting it. This is I cap plus, or you can put minus only, and this j cap over here. And ey is nothing but 7x plus 2y. The minus sign is common. This is our final answer in vector form. Usually, these questions also come in both x and y or x, y, z, etc. Is that clear? So if only one variable is there, it is very laddu. You just differentiate it with respect to that variable. But if two or three variables are there, each variable's differentiation has to be done separately. Each component will be separate, and then you can combine it in vector form. X component separate, y component separate, x component I cap, y component j cap, z component if at all k cap. Is this clear? Yeah. Sometimes this is also called as partial derivatives. I don't want you to unnecessarily confuse you with that partial derivatives. You will learn that in maths. For now, you just understand when you take the derivative with respect to a variable, other variables at that moment are constant. So when I differentiate with x, y, z is a constant. When I differentiate with y, x and z are constant. Is that clear? So forget the term partial derivatives. Yes, it is partial derivatives, but we don't need that term. Okay. So I think there is one question over here. If electric voltage is given by minus 3x square plus 4x, then in this region, what is the electric field? What is the electric field? Very laddu question, guys. Come on, do this. If voltage is given, find the electric field. Electric field is negative dV by dx. So negative d by dx of minus 3x square minus d by dx of 4x. So minus minus is plus, so plus 3, x square's derivative is 2x, and 4 will be there, x's derivative is 1. So it will be nothing but 6x minus 4 is the electric field. 6x minus 4 is the electric field. Come on, guys. Yes, 6x minus 4 is the electric field. So the electric field in that region is given by what? Come on, guys. 6x minus 4. I think there is a printing mistake over here. Most likely this minus sign shouldn't be there, or here minus sign should be there. Okay, one of them is wrong. So most likely, I don't know, most likely this might be, uh, you know, minus sign shouldn't be there. So the electric field in that particular region, you can say it is nothing but this whole thing I cap, if you put it in vector form. 6x minus 4 I cap. Is that clear? Then it will be correct. So 6x minus 4 will be the electric field. Remember, this minus sign was there. Minus and minus will cancel. It will become plus 6x, and this will become minus 4. So in such a case, that option number A will be the correct answer. Option A will be the correct answer. Absolutely clear? Okay. Yes. It's completely up to you. Kepon Chandra Poma. If you feel that problem solving and theory, you are fine, continue. But if you think, sir, I want the more competition, sir, I want the DPPs, sir, I want the coaching module for extra practice, sir, I want more in-depth classes, I want all your classes there and here, and I want the test series, and I want revision one shots towards JEE mains and then JEE advanced preparation, then you buy the Sigma batch. Otherwise, perfectly fine with going on YouTube. Okay? Yes, perfect. So that was that particular answer. And this year we had some amazing achievements. I would love to take a moment of appreciation and a sense of pride, which should be there for all the Vedantu students out here, because they are your seniors, and next year it could be you. And don't think, no, sir, what are you saying? I am not going to be on the board and all that. Let me just clear. No, guys, these students were also average students, but they worked hard for 2 years, 1 year, etc. And that's why they are here. And many of these kids also did extremely well in their Olympiads or boards or everything. And they never prepared for boards or any other exam. They started their preparation for a main exam like either JEE or Olympiad or something like that. And everything else was a byproduct, be it the CET entrance, be it the board exam results or any other exam result. So start your journey early, and if you are looking for something, then yes, best thing to do is go to an offline batch. Many Vedantu learning centers are there around you with personalized coaching, mentorship, tests and everything. So many branches, so many cities we are present in already, be it Karnataka in Diksha or Andhra, Telangana, Tamil Nadu, Maharashtra, and also in the north. But if you say that, no, sir, I want, online batch, that option is also available for you. In the offline batches, 90% scholarship can be given based on the test scores which you give, which is called as a scholarship test, IVSAT. So go to the center, book a, slot over there. The best way to book a slot, oh my God, okay, this video is still playing up. Okay, sorry. So as you're watching this particular video, go down into the description box, you will see it. Yep, go down. You will see it right over here. Our offline centers, book a visit. Better to book a visit and go there. Enter your name, grade, everything, your preferred city. So many cities are there. And yes, book a slot, give the test, see what scholarship you are getting, and you can think of a batch. But no, sir, I don't have any offline center, or maybe I want online batch. Then you have the Sigma batch for 2026, which is a proper online batch where I, along with PNJ sir, Diksha ma'am, Namrata ma'am, Pahul sir, and so many other amazing teachers are going to be a part of this pure English batch. And you have three different combos. One is the pure Sigma batch with all the lectures, test series, DPPs, assignments, everything. But some of you might want some revision flashcards, small. So that combo is there at an extra 1,000. And you want the books also, then that's for 8,999, the hard copy, which will be provided, couriered to you at your doorstep. Okay, so the batch is going to start on 16th of June, right? So make sure that you are in this batch, a live batch with complete guidance, mentorship till JEE advanced. Okay, it's not mains batch, it's a mains plus advanced batch, which will be taking you through this journey online. Okay, thank you so much. I hope you enjoyed. Like this video if you've forgotten. And yes, the answer to the homework question should be there in the comments. I've already told you the homework question. Okay, so please mark it. Next session again, every day 8 o'clock. You are going to have physics, chemistry, maths, 12th standard syllabus. Every day 6 o'clock, physics, chemistry, maths, 11th standard syllabus. Okay, in a cyclic order: physics, chemistry, maths, physics, chemistry, maths. Okay, see you. Next topic will be dipoles and torques and dipole moment, everything. Okay, bye bye.